Today's problem, number of paths in a matrix with k coins. Difficulty is medium, accuracy is very low. In this case, I can see why the accuracy is low. This is a harder problem on the, this is on the harder end of medium. And, let's just read the problem first. You are given a matrix of size n by m, where each of the cells contains some coins. Count the number of ways to collect exactly k coins while moving from the top left cell of the matrix to the bottom right cell. From a cell ij, you can only move to I plus 1j, which is down, or ij plus 1, which is right. You can move down or right. Okay, it is guaranteed that the answer will not exceed 32-bit integer limits, okay? So here's an example of, let's see, k equals 12. Here's the matrix. How can you get that? Let's see, 1, 3, 9, 11, 12. That's one way. What else? 1, 3, 6, 11, 12. You can get it that way. This one, you can't get it. There's no way to get 16. Okay, constraints. K is going to be between 1 and 100. N and M, height and width of the matrix, also between 1 and 100. The values in each cell of the matrix will be between 0 and 200. That threw me off on my first approach. Just I kind of glossed over it. The examples don't give the examples don't include cells with zeros, so it actually is possible to get a path where you get all of the coins that you need early on, and then you just follow paths with zeros the rest of the way. So that's a possibility. Expected complexities, n by m by k. Okay, right. Auxiliary space, n times m times k. Okay. And then we'll look at why do we need that, as opposed to it being just like n times m. Topic tags, dynamic programming. Recursion. Matrix, yes. Backtracking, yes. Okay. My first effort on this was just to do a depth first search, and it almost worked. It did time out fairly close to completing, but okay, so we do need the dynamic programming, the backtracking. Let's take a look at this. Let's scoot this over a little. I created some class variables here. One is for the matrix. One is for the height, one is for the width, one is for the DP array, a memoization array. So, yes, top-down dynamic programming. I mean, it's a recursive solution, but we're memoizing the solutions. All right, in the main routine, set the matrix variable, the class matrix variable to the matrix, set the height to the length of the matrix, set the width to the width of the matrix. Now in this one, we need to set some kind of indicator for the memoization array to tell us whether or not we have we've already computed this cell. And you can do it with loops, to initialize everything with -1, or you can declare it as an integer, a 3D matrix of integer types, integer class types. Now that's going to initialize everything with null, so we don't have to initialize anything. All right, now we do the depth first search. We do the depth first search starting in the top left corner, index 0, 0, and pass in k, which is the number of coins that we're trying to get. Okay, I feel like there was something else I wanted to say about that. So this is why the time complexity of the auxiliary space is n times m times k. That's not what I wanted to do. Because for each cell in the matrix, it isn't enough to say, all right, from this cell, we have n successful paths. Because it depends on how many coins are we looking for from that cell. So you have to take that into account as well. All right, base cases. If either index is beyond the bounds of the array, then there is no valid path. So if r is greater than the height or c is greater than the width, returns 0. We don't have to check the indices against 0 because we're starting in the top left, and we can only go right and down. There's no way to get to 0. Number 2, if remaining coins becomes negative. Now, at each cell, we're going to subtract the number of coins that we find in that cell from K, and then continue with the search with a smaller K. But if we subtract so many coins that K goes negative, that path isn't going to work. So return 0. All right, next. Did we reach the bottom right cell? That is, the row index equals height minus 1, the column index equals width minus 1. All right, if the current K, and that is the input, by the way, current K is the input to this recursive routine. If current K equals the value of the bottom right corner, then return 1. We found one good path. If they're not equal, return 0. We didn't find a good path. All right. Now, before we do any recursion, we're going to check and see if the result for this state has already been computed. So that is memo at row, column, current value. If that is not equal to null, just use the value that we've already computed. All right, recursive step. We calculate the number of paths that we can get if we move to the right. That is, leave the row where it is and look at C plus 1. Also, adjust current K to subtract the number of coins in the current cell. Next, a recursive call to see how many good paths we can find if we move down. That is, leave the column where it is, add 1 to the row, subtract coins in the current cell from the current K. All right. So the value in the memoization array at row, column, current K will equal the number of good paths to the right and the number of good paths going down, and we'll return that. We'll also put it in, well, we already put it in the memo array, and then we'll return the memo array. That should work. It's a depth first search, but the recursion, it takes too long. So we convert it to dynamic programming. The difficulty of this is that it seems like a 2D dynamic programming problem, but it isn't. It is important for each cell. The number of good paths that we can find from that cell depends on the number of coins that we're looking for. Now, they do give us a tip-off here in the time complexity and auxiliary space by saying, you know what you're going to need, n times m times k, right here. So let's try and run this, see how it goes. Let's try it. Okay. I did say I tried a couple of approaches that didn't work. It's kind of, I always hate to I hate to see that, but anyway, I try to share the lessons learned, things that will work for a problem like this and things that won't work. So what we've done here will work. I hope you will like the video and subscribe to the channel, and we'll see you next time.